Good evening, students. I'll start with the class. In the previous class, we had seen the normal basic properties of vectors. Today's class, we'll see we'll try to compare rotational motion with linear motion. Okay, or consider any suppose body, any rigid body is suppose spinning. Okay, now consider this is spinning along the axis. Okay, this whole circular is at one, this whole body is at one point, but it is rotating, it is spinning along this axis. So this movement is taking place. We'll draw it in this way, like now this may be the center. For reference, I'll take. Okay, whenever there's anything rotating, obviously it will be called as a rotational motion. Now your displacement means what? The movement will not be in terms of normal meters, because now the change in the body is taking place in terms of angle also. It's not only linear, but it is whenever angle is involved, we'll be using the word angular velocity, angular displacement, angular acceleration. This may be linear. This is in terms of line. Okay, this, if you consider like a straight line at every point, this will be considered as S. That is the normal displacement. But this is in terms of angle. So now there will be two things. One could be linear, the other one will be angular. So whenever body is moving in a straight line, it is called as a linear displacement. We done the board. Just shifted this. And which letter do we use? We use S for linear displacement. Whenever any, this is for rotational. This may be used for translational. In this, it is called as angular displacement. In terms of rotation, the movement of the object is described in terms of not meters, but in terms of angle. Angular displacement, that is theta. Second thing we'll see for linear, what it is called linear velocity or normal velocity only we use. And that is nothing but displacement upon time. Okay, change in displacement upon time. And that is denoted by the letter V. So this is linear displacement, you can mention. Here it is called as the angular velocity. That is angular displacement upon time. And denoted by the letter omega or W. You can say W only, no issues. Now there are two types of velocities. We know that one is instantaneous velocity. which is at exactly at that point, that is given by ds upon dt, and the other one is, okay, first one is the instantaneous, and then the other one is average velocity. Here we take the derivative. Here we usually take the final minus initial, delta s upon delta t, change in velocity upon time. In this case, for angular velocity, instantaneous angular velocity will be dw upon dt, and average angular velocity will be, sorry, this delta t, theta. Theta is changing now, angular displacement, to delta theta upon delta t, change in angle upon time. How much the angle is changing with respect to time will give you angular velocity w. The third thing is, here normal it is called acceleration. That is what? Change in velocity upon time. Here the letter used is a. Here acceleration is used by the letter alpha for angular. Same thing, change in, now this is angular velocity upon time. Again, instantaneous one is dv by dt, and average one is delta v upon delta t. Here instantaneous acceleration alpha will be dw upon dt, and average one will be delta omega upon delta t. Whatever these terms we have studied in terms of straight line, okay, in linear, same thing it is in terms of angular, only the notations will change. Whenever there's a rotational motion, everything will be in terms of theta. So instead of v, it will be w, instead of a, it will be alpha. The same way there will be the fourth one, that is the momentum. Now before that, there's a force. Fourth one is force. Straight away, force is given as F. In this side, it is the word used is torque, and the symbol is tau, something like this. This will study in detail what is this torque. Anything that causes, any force that causes an object to rotate is called as torque. Like when you want to open the door, okay, so when you apply force, it makes the door rotate. It will move in a angular direction. If you compare with the edge of the door, no, the angle is changing. It moves in a circular, no, semicircle type. So that force which causes any rotational motion is called as torque. This we have to study in detail. Then the fifth one is linear momentum. In we have seen m into v, linear momentum. And angular momentum is given by the letter L, which is R into P. Okay, this is normally a dot product. This will be a cross product. So these are the 5 terms which we can compare. It means linear versus rotation. So this all the terms are used for rotation. We will study that now. This we had already done all in the previous chapters. Now motion in a straight line. Okay, this term. Now this you have to study in detail. Detail in the sense you have to know what they are in rotational motion. Okay, the first one, what is angular velocity? You can just give it as angular velocity. Angular velocity is nothing but angular displacement per unit time. Suppose from here to here, if the movement has taken place, this is theta, and this is the time taken to move from here to here, this point to this point. Okay, then denoted by which letter? So this is for average. This is instantaneous. Now let's see what is relation between linear and angular velocity. Linear velocity is v, angular velocity is w. What is linear velocity? Nothing but v is ds by dt. Just now we have seen the formula. We're just checking for the instantaneous one. Okay, v is nothing but ds upon dt. Change in displacement upon time. This is normal velocity formula. Change in s is for what? Linear one. Now we have to see what is the relation between linear and the angular. So this is what you can consider to be an arc. How much distance it has been covering? Suppose s distance. Draw it again here. So from here to here, s distance, suppose if it has covered. And this is full circular motion, so definitely this will be the radius. This will be the radius r. So if we are calculating for this, we always know arc length is always equals to radius into theta. This is the arc length formula from trigonometry. Okay, any arc of a circle is r into theta. So as per that, what is here? S will be r into theta. This arc is nothing but of length s. So just put it there because this we are calculating for a small area. So V will be, substitute here. You have to take derivative of r theta. Radius is always constant, so you can always remove it out of the sign. R can always be removed out. Now what is d theta upon dt? Omega. Okay, even if you, anyways we are calculating for instantaneous only. So this change in angle upon time is nothing but your angular velocity. So that is equals to W. Therefore, the relation between linear and this is given by relation between linear and angular velocities V equals to R times W. This is linear velocity, this is radius, and this is angular velocity. Next we'll see what is angular acceleration. Okay, from any distance if it is covering, the velocity is changing, no? Means what, suppose from here to here, I'm just going at some constant speed, okay, or constant angular velocity, then acceleration will be 0. But if from here to here there is a different angular velocity, from here to here different, okay, then obviously we'll say something is accelerating or deacceleration. Whenever velocity changes, acceleration will come into picture. So acceleration is nothing but change in velocity per unit time. So which letter is used? Alpha. So alpha is given by dw upon dt. Make a note for fixed axis of rotation, the direction of omega does not change with time. Means what, if you have a fixed axis, consider your fan only. They have one particular direction only. Okay, your fan would be obviously rotating in one particular direction whenever you have a fixed axis. It will never start suddenly moving in some other direction. So for any fixed axis of rotation, for example, you can consider fan. Your velocity, speed of the fan will change based on your regulator, whatever you want to do, but direction will never change. Okay, the direction of omega does not change with time. So for fixed axis, then when direction does not matter, you can consider this as a scalar quantity. Usually this is what a vector quantity, because velocity is obviously a vector quantity because direction matters. But for fixed axis, you can take a scalar one because direction does not change. So whenever there is no need of change in the direction, when direction is constant, means it becomes a scalar. It's a fixed thing. So angular acceleration is nothing but change in angular velocity per unit time. Next is, you see what is torque. Now consider your door only. There is no, this is fixed. Okay. So here there will be a handle or whatever. Obviously, you'll apply some force. It's going to rotate. It's going to go inside. If the door is closed and you're applying some force here, okay, from this side, okay, perpendicular to the door, so then your door will rotate. Imagine you're trying to put a force here at the edges on the hinges. These are called as hinges. Okay. Imagine you're trying to put some force on the hinges of the door. Obviously, the door will not go inside on the fixed side. If you put, just give a try, okay? If you just even touch a finger at the edge towards the end of this, the door will move. But here, if you are trying to put pressure, force towards the end side, maybe here, you will need extra force to push. So even the direction from the fixed point also matters. More the distance, no, less will be the force needed to push. Okay. Yeah. So torque is nothing but any force which creates a rotational motion. So you can write torque as, on the textbook they have given it as rotational analog of force. Also called as, you just write a moment of force. Also used as moment of force. So just the explanation part. Okay. When we apply force on handle of the door, the door turns. More the force, more is the turning effect. When the distance from, when the distance of force from fixed point is more, less force is, or I can say more turning effect. As I've told you, if you put force on the handle, it will means same amount of force. If you try to touch here, the door will turn more compared to if you touch your finger at the towards the hinges. This the force which causes this turning effect is called moment of force or torque. Okay, so this is the basic explanation of torque, denoted by tau, like a T. Okay, well, basically like a C and then like this. Torque depends on two things. First thing is how much of force you're applying. Okay, it depends how much force and where you're applying the force also. Simply I told you, you cannot just go on, keep on pushing at the fixed end, at the hinges, the door will not turn. It depends where exactly you're applying also. So how much force and where exactly you're applying. So the perpendicular distance, okay, of the force of, of the line of action, this I'll explain, of force from the axis of rotation. Now imagine something is fixed at this end. There's a rod. Okay, and now you want to turn it around this. This is movable, suppose it can be rotated. Now this, if I apply, maybe the next moment it will move this. Okay, and then after some time it will come. So it's rotating round and round across this fixed point. Imagine you're trying to apply. Now this is when maximum, when there is a perpendicular force. Okay, whenever you apply, you notice it will give you a maximum effect. Imagine you are just trying to apply this force this side. You're trying to put a force on this rod from this direction. Will it make any difference? Obviously no. Okay, for this force, rotation will be 0. It is not going to make a turning effect at all. But if you, this side also you can apply any direction also, but if you notice, for this, no, perpendicular, when you apply, it will create a maximum effect. Whenever you have a perpendicular distance, okay, whenever force is perpendicular, it will make a maximum effect. Now in terms of any rigid body, this is a fixed axis and this is the body. Okay, now I'm trying to rotate this. if I'm applying a force here towards any angle also, and this is the fixed body at this point, and force I'm applying suppose this side. Now how much magnitude also depends, how much force I'm applying for this to make it move. Maybe I'm just considering slant force, but to measure this distance I have to take from here to here, the perpendicular distance. So this becomes a R or maybe D. The line of action of force means this is line of action. Less the distance. Now if you notice, this circle is attached to one fixed rod, and this maybe it's a disc. So you're just trying to push this and trying to rotate. Imagine you just reduce the distance, the force you're applying here. Less the distance, more the force you'll have to apply. But if you are increasing the distance towards the edge, if you try to put a force, it will rotate more. So the perpendicular distance from the fixed point also matters. This distance. Okay. So these are the two things that matter. How much force you're applying and where exactly you're applying, how far. So torque formula is given as, it depends on two things, the force and the distance. Instead of D, some places you'll come across it as R. Okay, we'll use R only. R is nothing but meant for distance. Use this other way around, tau, because even this will matter, R into F. Considering the direction this side, we are taking anti-clockwise direction. If we make this ulta, we are considering the force is applied on the other side. This is for normal direction of force. If we use from outward force, no, this is what now we are trying to put this inward force. From here I'm applying. If I put this side, it means from the other way around the force is coming. Because for vectors, I told you the direction matters. If you want to write in terms of what is A cross B, this is also vector. So tau will be, in case magnitude you want to write, then it will be R into F sine theta. So this is the magnitude. What is R? R is nothing but position vector, where R is lying. This is the position which denotes position vector of the point on which force is applied. F is nothing but magnitude of force. And theta is nothing but angle between R and F, capital F. Unit of force is, SI unit of torque is Newton meter. And dimension M. To solve some problems based on the talk. First question. Find the torque of a force seven I cap plus three J cap minus five K cap. The force is acting on one particle whose position vector is I cap minus J cap plus K cap. Your angle is not given. Okay, only two vectors are given. Position vector means R bar. Force is given as 7 I cap, 3 J cap, 5 K cap. R bar is given as I cap minus J cap plus K. What is tau? What is torque has been asked. So we know that torque is nothing but cross product of this into this. Whenever angle you know between them, you can use that RF sin theta formula. How to find? Previous class only I told you how to find A cross B. I, J, K. Then we have to put the coefficients. So we'll have to put coefficients of R first. 1, minus 1, 1, 7, 3, and minus. Now refer your previous vector formula and just try to write I cap, close the row, column, just try to solve. I've already taught you all how to solve a vector. Just close the row, column, and then cross multiply. So if I close, first I have to write I as it is. I have to close the row and the column attached to it. Then minus, middle sign always minus, I told her. Now close this column and the row, whichever is attached to J now. So 1, 7, this is what is remaining, you have to write here. And for K cap, close the row and the column. This is what remains.
Please consider board properly.
One second. The third one is K cap. Now we have to cross multiply. I get now this into this. -1 into -5. Middle sign is always minus. 1 into 3. This always you have to start first. You cannot do this minus this. 1 into 3. J cap 1 into -5. 1 into 7. And then K cap 1 into 3. Middle sign is always minus. Now simplify. Minus into minus plus 12 J cap. This is torque. This is the answer in terms of vector. Second one, calculate turning effect of force for the following. This is 10 Newton. And this is 2 meters. The radius is 2 meters. And F is given as 10 Newton. Even if not mentioned, then F Newtons means nothing but force. Now turning effect, whenever you ask to calculate, it means the same thing. Turning effect of force is nothing but torque. Now vectors are not given. We cannot use this formula. So what is the angle here now? This is 90 degree. Force is given as 10 Newton. R is given as 2 meters. The perpendicular distance. So what is the other formula? RF sin theta. This will be 2, 10, and theta is 90. You have to always take this normally perpendicular, okay? Perpendicular distance. Given also the 2 points which I have given. RF torque depends on 2 things. One is the magnitude and the second one is the perpendicular distance. So this normally you have to take the perpendicular one. This will be anyways perpendicular, so straight away 2, and this is sin 90. Sin 90 is anyways 1. So this is 20. Okay. Unit will be Newton meter. This is the first one, suppose. And the second one. The diagram is like this. This is fixed at this end. This is the force applied. Newton of force is applied at an angle of 37 degree. And from here to here is 1 meter. Find the turning effect. Means something, this rod has been pulled. So how much turning effect it will cause? Now we have to always take the perpendicular force. Okay, because we have to make sure R and force should be perpendicular to each other. So we'll find both the components, horizontal and the vertical. 10 cos 37, this will be, and this will be 10 sin 37. Obviously, this will make no effect on the turning. If I'm trying to pull this rod this side, you cannot make any changes. Before also I have told, in the line, the same one in the line of this, if you make, there's no point. You have to take the perpendicular one. You have to take the angle as 10. Okay, or even if you don't use this concept also, if you are using this formula, automatically you will be able to solve. If this is confusing for you, just ignore this part. What is the formula? RF sin theta. Why do we take this? Because sine is the perpendicular. How much is R given? 1 meter. How much is F given? 10. Angle is how much? 37. We need to find what is sine 37. Sine 37, instead of using on the log book directly, there's one triangle which we have done. There's a fixed triangle for that. Whenever this is 37, you have to remember this triangle. One is, I think, with 53 I've done, other one is 57. So this side is always 3, this side is 4, and this is 5. So sine 37 is always opposite upon hypotenuse, which is opposite side 3. Hypotenuse is 5. So directly you can remember sine 37 is 3 by 5 and cos 37 is 4 by 5. So directly substitute and calculate. So that will be 6 Newton meter. So even if you don't do this, it's fine. Only angle between R and force you have to take. So this was about calculating torque. One more I'll give with a point. If it is given, then you have to just convert this. A force F is equals to 2I cap plus 3J cap minus K cap is acting at a point 1, 2, 2. Find moment of force about the point 0, 1 and 3. So basically now there are 2 points. Zero, 1 and 3. So the force is acting at this point. Okay, and this is maybe the fixed end. At this point you have to calculate how much of torque is generated. Moment of force means torque. How much of turning effect is generated over here. Force has been applied here. So obviously turning effect will be caused here. So what is the distance? Here, this I'm just taking tau equals to how much? So you have to just basically calculate R now. So R also you have to calculate in terms of vectors now, because this is vector. So the other one R also has to be vector. So any point can be converted into vector. This will be 0 I cap. Okay. O bar I'll consider because I've taken the point as O. 1 J cap. This will be 3 K cap. Same way P bar will be what? 1 I cap plus 2 J cap. So R is nothing but the distance between this and this. So in terms of vector, position vector, R bar will be nothing but P bar minus O bar. When you open up the bracket, 1 minus 0 is anyways 1. 2 minus 1 is 1 J cap, and 2 minus 3 is minus K. So this is R bar. And F bar is already given. So tau is nothing but R bar into F bar. So I, J, K. Now put R bar 1, 1 minus 1. Put F and then calculate. After that, just normal determinant solving part. Answer, you calculate and see, it should be giving you 2 I cap minus J cap plus K cap. Just in case magnitude of force is asked, no? Magnitude, this is what vector form. Suppose magnitude is asked just the value, and you have to do like this, 2 square. All the coefficients you have to square. So 4 plus 1 plus 1 root 6 Newton meter. Root of that. So this was about torque. Torque is nothing but distance into force. The perpendicular distance. So two formulas. One is this. This you have to solve using determinant form. ijk. In the other one, if angle is given, you have to use this. This directly you'll get in magnitude form. Next topic is angular momentum. Linear momentum is given by P, which is mass into velocity. So this is what, nothing but whenever anything is rotating, the linear momentum which causes spinning effect, it is called as angular momentum. So rotational, analog. Analog means just a way of representation. How in velocity, finally the logic is same, displacement upon time, but we are just giving them different names. Okay, one is in terms of linear, we are using V. W we are using for angle because it is in terms of angle. But the logic, the main thing, change in displacement or change in angle upon time, that remains the same. The same way, angular momentum is also nothing but just the way of writing, rotational way of our linear momentum. So denoted by the letter L. Angular momentum of particle is given as R into P. All are vectors. We want to write in terms of magnitude, RP, sin. Again, where R is nothing but a position vector. P is linear momentum. And theta is angle between R and P. Next, we'll see what is the relation between torque and angular momentum. I will just do, it's a small differentiation rule. Just see, you all want to study or not, but I just want to show how it arrives there. Okay, if it's done in your college, you want to study it, up to you. Suppose how we derive, you can directly remember the relation on the end formula. Okay, just see how it appears. Just now we saw that what is this linear momentum is nothing but this angular momentum is nothing but R into linear momentum. Just basically you're just multiplying extra with R. Now let us differentiate on both the sides. When you differentiate, means you have to take derivative on both sides. So this will be dl upon, always we differentiate with respect to time. So this will be dl upon dt. Now these are both u into v. Those who are math students will come across this part now. Towards the end of the this in 11th standard itself, there is something called as u into v rule. Whenever you take derivative of two things, no, when there's multiplication, you always copy paste the first one as it is and give one at a time a chance. You take the derivative of the second fellow. Then what you do is copy paste the second fellow, take derivative of this. So it's like there is some serving of food taking place. The first one remains there only, gives chance to the second one. Then the second one remains there only, gives chance to the first one. So that way, there are two things now. So we copy paste R as it is. We take derivative of this. So this one gets the chance. Both don't never get a chance at the same time. Huh? Plus, then P remains. Then to take derivative of the other. So this is a differentiation rule. This is nothing but change in distance upon time. Change in the distance upon time is nothing but velocity. What is dr upon dt? Change in displacement upon time is nothing but velocity. And what is P? P is nothing but a linear momentum, which is nothing but mass into velocity. Straight away, that will be V. I can keep it that way only. Instead of this, P only you keep, no problem. So this is change in velocity, change in distance upon time is velocity. This is fine. There's a cross product. Huh? Now this P I'll put mass into velocity into velocity. P is nothing but mass into velocity. So anytime you take cross product with itself, always answer is 0. A cross any vector cross product you take with itself, always 0. Yesterday's class also we have seen, previous class, I cross I will get 0. J cross J is 0. With itself is anyway 0. So this value is 0. So dl upon dt is and this is nothing but what is change in this upon force. dp upon dt is nothing but force. Change in linear momentum upon time. This we had seen the previous chapters also. Okay. So what is R into F? Nothing but torque. This is equals to force and this is equals to torque. So this is the relation between angular momentum and torque. If you want, you can directly remember only this box. Change of angular momentum per unit time is equals to torque. If you ask what is the relation between this is the relation. Change in angular momentum per unit time is equals to torque. acting on it. Angular momentum, was with reference to one particle. Suppose if we have many particles, total angular will be what? You may consider it to be L. L will be what? Means there are many particles and every one has L1, L2 like that. So L will be what? Sum of all the particles. So if I want to write in general what it is, addition of all L. Only this is changing. So I just write it as I. So these small letters. Okay, total is nothing but sum of all the small Li. The previous one we have seen that Li is same as, what is the relation between linear and this? Angular and linear is, this is the relation. So you can just substitute it here in terms of linear if I want to know. This will be Ri into. This is the angular momentum for system of particles. And torque for system of particles. Torque due to center of mass. Okay, usually considered as external torque. The same as change in angular momentum upon. Okay. The same one, same formula, you just have to use the word external. I've told you whenever there's a center of mass, we consider it's like acting, all the forces are acting together towards the center. So in terms of force also, it's like external forces are acting towards the center. So we just use instead of center of mass, the word external. That is given by dl upon dt. What will be the torque in the main center inside it? Suppose internal one will always be equals to 0. Okay. It's equilibrium of a rigid body. So there are two important types. One is called as a static equilibrium. Equilibrium means there's some word equilibrium itself means there's a balance. Okay, there's a balance between something, or it is at rest. Maybe the body is not moving basically. So when is a rigid body at equilibrium, there are two things to be considered. First one, when it's translation motion, in the translation motion, total force acting on the body is zero. Or you can use the word net force. Net force acting on the body is zero. If there's an object, someone is trying to pull this side, someone is trying to pull this side. So net force plus 10 minus 10 will anyways make it zero. Okay. So total force on the, now you may say, oh, there is a force applied. No, the total force it means. So the body will anyways not move. If there are equal and opposite forces acting and cancelling out each other, basically it means total force acting on the body is zero. It is the word net. Okay, so body there will be no change. Okay, in the rigid body. So it means from all the directions, whatever the forces are there. So net force means summation of all the forces. So even from x direction is also zero. From y direction is also zero. From z direction should also be zero. On every single particle, the net force acting should be zero. And the second thing, even for rotational motion, all the rotational, so which is the word we use for rotational instead of force, we'll have to use torque. Total torque, the turning effect force, total torque on the body is zero. Okay, so basically the linear force as well as the torque, which is the turning effect force, should be zero. So total torque should be zero. So all the, even from the x direction, total torque from the y direction also, total torque from the z direction also should be zero. Sum of all, like there are many particles, no? Maybe this is the x direction. So everywhere, maybe this side, whatever are coming from the x should be balancing out at every particle, and net, the summation of all the forces should be equals to zero. This is your force. Maybe from the y direction also, this basically this side, maybe from z also. So from all the directions, the forces together acting should be zero. So if these two conditions are satisfied, then the body is said to be under rigid, this under equilibrium, static equilibrium. Now there's something called as a partial equilibrium. In this, what is happening? Both there's no translation motion also forces, there's no rotational changes also. Next is the partial one. There are two things, case 1 and case 2. A body is said to be in partial equilibrium if, first thing, there was static, both were zero. Here one, what is happening is one of them might be zero. Your translation will be zero, okay, forces, but rotation might take place. The second case, rotation might be zero, but there will be translation motion. So first case, in translation equilibrium, but not in rotational equilibrium. This means F net is zero, but torque is not equal to zero. Total torque, there will be some torque. Example, something is fixed, okay, and I'm applying a force here, and I'm applying force here. Now what is going to happen at this fixed point, maybe whatever it is, this is just spinning. It is only going to spin. Is this rod moving this side, or is this rod moving this side? When is translation motion? Whenever there's a linear motion, basically it shifts from one place to another, or maybe from here to here, or maybe from here to here in parallel path. But now it's only rotating, purely rotating. So torque is not zero, okay, because this might not be equal and opposite forces. It might be something different. So there is rotation is taking place, but linear is not taking place. So that is one case. The second one, it is in rotational equilibrium, but not in translational. Means total torque is zero, all the forces, torque, and here net is not equal. Consider there is one rod. In both the cases, there is a downward force only, F1 and F2. Now what is going to happen? This rod is going to move translationally. Or maybe they are balancing out each other irrespective of that, but there is no rotational motion taking place. Only translation motion takes place. There is no rotation. F net is not equal to zero. I'll stop here because next is the principle of moment of lever. I'll do it in the next class. Then center of gravity, then moment of inertia is left. The last part, that is the parallel axis and perpendicular axis, that has been deleted from the chapter.